Okay, so now I want to do this problem. Um, I will just say at the outset, this is a weird problem. And why do I say it's a weird problem? Well, it's a sort of non-conservative conservation law. So let me come down and look at the problem. So what does it be? Or look at the PDE and talk about it for a little bit. The PDE says the t derivative of u plus u times the x derivative of u is equal to 1. If we write this in the so-called conservative form, this will become this. Okay, and let's sort of think backwards. How is such an equation like this derived? In fact, let's just forget about the u squared over 2 and do this a little more generally. If I have something like this, let's try to think of where such an equation, how such an equation would come into being. Well, usually we're like integrating over two arbitrary points. So if I integrate over two arbitrary points, I'm going to have something like this on the left-hand side. It's the t derivative of u evaluated at xt plus the x derivative q of u evaluated at the point xt. All of this derivative is done with respect to dx. And on the right-hand side is going to be the integral from a to b, 1 dx. Okay, this is valid for all intervals a to b. Okay, so now what's going to happen on the left-hand side here? On the left-hand side here, this is going to be the integral from a to b, the t derivative u of xt dx. But notice what's going to happen by the fundamental theorem of calculus. This is going to be q of u of bt minus q of u of at. And now on the right-hand side, this is just going to be equal to b minus a. So in other words, over any interval a and b, we're going to have the integral from a to b. This is going to be the change in u in this interval is going to be equal to b minus a plus q of u q of u evaluated at at minus q of u evaluated at bt, like this. Okay, so now this is kind of how the conservation law reads. Okay, so now let's think about how we're dealing with shocks. So if you remember what happened last time when we were dealing with a shock, we imagined we had some solution going this way, then there was a discontinuity, and then the solution was something else going this way. Let me use a different color over here. Okay, and this is going to be for a fixed value of t, and we called this xs of t. And how did we figure out what that shock was? Well, we looked at an interval around the shock. Let's say this is the interval a, and let's say this is the interval b. And we said, okay, well, we're going to assume that across the shock, our solution satisfies the same conservation law. So in other words, what we did was we computed, we said across, if I look at a over b, if I look at this, if I look at the integral from a to b, this, a to b, u of xt dx, well, this should be what I'm expecting it to be, which is b minus a. Before there wasn't the b minus a term, but here it is. So we're going to assume our solution is satisfying the same shock condition. And this is going to be equal to this plus q of u of at minus q of u of bt. Okay, now how did we handle this integral over here? So for this integral over here, we split it up into an integral from a to the shock location and b to the shock location. We applied Leibniz's rule, and we did a whole bunch of stuff that you can go back and look through. It's all going to be the same over here. And we ended up with xs dot, remember this is the shock location. The shock location is going to be equal to this times the jump in rho minus the jump in q across the shock plus plus q of u of at minus q of u of bt. Okay, that's what the left-hand side is. That's what this is. That's independent of the b minus a part or anything else. That's just using the Leibniz rule. And now for us, this is going to be equal to b minus a, and I don't have enough room. It's going to be plus this part right here. Okay, but the part there and this part are equal to each other, and so overall, this equation becomes xs dot of t times the jump in u minus the jump in q is equal to b minus a. Okay, now this is true for any interval that passes, any interval that contains the shock location. In particular, it's true for very, very short intervals, like intervals that are epsilon long. And so I could say this is equal to epsilon. And so now what I have is I have xs dot of t is going to be equal to the following, is going to be equal to epsilon over the jump in u plus the jump in q over the jump in u. And since this is true for every value of epsilon, as epsilon goes to 0, it implies that we have the same xs dot of t is going to be this same formula. Okay, now let me just point out that the whole reason that we have this formula for the derivative of the shock location is because that makes sense physically. When we're dealing with a conservation equation, that clearly makes sense physically. It's completely possible in this sort of made-up scenario that I have that this is not the physical thing to do. This is going to get us a correct answer. This is going to get us a correct answer that's consistent with what we've done so far, but this is different from the conservation laws that we've seen so far in that it's non-homogeneous. Okay, so I want to point that out. Maybe this makes sense physically, maybe it doesn't make sense physically. All of that's going to be determined by the actual problem domain of the function, or the PDE, when we're looking at an actual physical problem. But I think, this would model some sort of this problem models some sort of aspect where all along the domain there's this sort of constant source coming in, and in that case I think this makes sense. This makes sense physically. Okay, so let's come up here and let's get to work. All of that was just to verify that we can use the same formula, the same method to find the shock location as we have been using. All right, so t dot s is going to be equal to 1. T of 0 is 0. Oh, let me do the Cauchy curve first. It's going to be the x-axis. Okay, x dot s is going to be equal to z, and x of 0 is going to be x naught. Now look, z dot is going to be equal to 1 this time, and then z of 0 is either going to be 1 or 0 depending on x naught. Okay, so to the left of the origin we're going to be 0. To the right of the origin, to the left of the origin we're going to be 1. And to the right of the origin, we're going to be equal to 0. Okay, so now let me solve these characteristics for x naught less than 0. For x naught less than 0, we're going to have t of s is equal to s. Okay, now z of s is going to be a little bit different. It's not going to be just whatever. It's not just going to be whatever z naught is, because z dot is equal to 1. So z of s is going to be equal to s plus 1. Now, x of s, if this is true, x dot of s is going to be equal to s plus 1. And so x of s is equal to s squared plus s plus x naught. Okay, so the sort of characteristics that we're going to have here, these are going to be characteristics. The horizontal variable is squared and the vertical variable is not. So these are going to look like square roots, or like a square if you rotate the axis by 90 degrees. So these are going to look like squares, or square root curves. Again, I shouldn't start when x is equal to 0, x naught is equal to 0, but I'll do the dashed line one there. And so we're going to have things that look roughly like this. Okay, now for the blue side, if x naught is greater than 0, what's going to happen here? Actually, I need to I'm going to redraw these. I'm going to make them look. These are just qualitatively what they're going to look like. Not don't get too hung up on these being the right graphs. In fact, graph these in Desmos and it'll look even better. Okay, for x naught greater than 0, t of s is equal to s. Z of s is still going to be s plus z naught, but here z naught is 0. And so x of x dot is going to be s. So x of s is just going to be s squared over 2 plus x naught. And so now I see that there's going to be a shock. So I can solve for the characteristics on the orange part and solve for what the solution is going to be on the blue part. So let me go ahead and do that now. So over here, u of AB, again, if AB is an arbitrary point on this characteristic, this is going to be equal to s plus 1. Okay, well, what is s in terms of A and B? Well, this is just going to be equal to t plus 1. Because s is equal to t. So this is b plus 1. Okay, so over here, u of xt is equal to t plus 1. Okay, similarly over here, u of ab is going to be equal to s, which is just equal to t. Okay, so now let's look at the shock. So now I want to find the location of the shock. I have enough room to do that over here. So xs dot of t is going to be equal to the jump in q over the jump in u. And remember, q of u for this problem, if I come back up here, q of u, writing this conservative form, is u squared over 2. And so this is going to be equal to 1/2 times u to the right of the shock plus u to the left of the shock. U to the right of the shock is t, u to the left of the shock is t plus 1. Okay, so now I've got so now xs of t is going to be 1/2. I'm just going to integrate this with respect to t. So t squared, the antiderivative of, 2t, the antiderivative of 2t is t squared. The antiderivative of 1 is t plus c. And I know that the shock starts at the origin here where t is equal to 0 and x is equal to 0. So it tells me that c is equal to 0. So that is the shock location. So then u of xt is going to be equal to t plus 1 when x is less than 1/2 t squared plus t, and it's going to be equal to t when we have x greater than 1/2 t squared plus t. Okay, and here we have it, a very strange problem, but that's the solution, or that's a solution. And I think for certain physical situations, at least the type that we're thinking about, it's the one that makes sense.